its crystallographic orientation notches. Wafers under 200 mm diameter have flats cut into one or more sides indicating the crystallographic planes of the wafer, usually a 110 face. In earlier generation wafers, a pair of flats at different angles additionally conveyed the doping type. See illustration for conventions. Wafers of 200 mm diameter and above use a single small notch to convey wafer orientation, with no visual indication of doping type. 24. Impurity doping. Silicon wafers are generally not 100% pure silicon, but are instead formed with an initial impurity doping concentration between 1013 and 1016 atoms per centimeter 3 of boron, phosphorus, arsenic, or antimony, which is added to the melt and defines the wafer as either Vulcan type or P-type. 25. However, compared with single crystal silicon's atomic density of 5,1022 atoms per centimeter 3, this still gives a purity greater than 99.9999%. The wafers can also be initially provided with some interstitial oxygen concentration. Carbon and metallic contamination are kept to a minimum. 26. Transition metals, in particular, must be kept below parts per billion concentrations for electronic applications. 27. 450 mm wafers. Challenges. There is considerable resistance to the 450 mm transition despite the possible productivity improvement because of concern about insufficient return on investment. 21. There are also issues related to increased into-die forward/edge-to-edge wafer variation and additional edge defects. 450 mm wafers are expected to cost 4 times as much as 300 mm wafers, and equipment costs are expected to rise by 20 to 50%. 28. Higher cost semiconductor fabrication equipment for larger wafers increases the cost of 450 mm fabs, semiconductor fabrication facilities or factories. Lithographer Chris Mack claimed in 2012 that the overall price per die for 450 mm wafers would be reduced by only 10-20% compared to 300 mm wafers, because over 50% of total wafer processing costs are lithography related. Converting to larger 450 mm wafers would reduce price per die only for process operations such as etch, where cost is related to wafer count, not wafer area. Cost for processes such as lithography is proportional to wafer area, and larger wafers would not reduce the lithography contribution to die cost. 29. Nikon planned to deliver 450 mm lithography equipment in 2015, with volume production in 2017. 31. In November 2013, ASML paused development of 450 mm lithography equipment, citing uncertain timing of chip maker demand. 32. In 2012, a group consisting of New York State, SUNY Poly /College of Nanoscale Science and Engineering, CNSE, Intel, TSMC, Samsung, IBM, Global Foundries and Nikon companies has formed a public-private partnership called Global 450 mm Consortium, G450C, similar to Semitech, who made a 5-year plan, expiring in 2016, to develop a cost-effective wafer fabrication infrastructure, equipment prototypes and tools to enable coordinated industry transition to 450 mm wafer level. 33. 34. In the mid of 2014, CNSE has announced that it will reveal first fully patented 450 mm wafers at Semicon West. 35. In early 2017, the G450C began to dismantle its activities over 450 mm wafer research due to undisclosed reasons. 36. 37. 38. Various sources have speculated that demise of the group came after charges of bidrigging made against Alani Kaloyaris, who at the time was a chief executive at the SUNY Poly. 38, 37, 39. The industry realization of the fact that the 300mm manufacturing optimization is more cheap than costly 450mm. Transition may also have played a role. 38. The timeline for 450mm has not been fixed. In 2012, it was expected that 450mm production would start in 2017, which never realized. 41. Mark Durkan, then CEO of Micron Technology, said in February 2014 that he expects 450mm adoption to be delayed indefinitely or discontinued. I am not convinced that 450mm will ever happen, but, to the extent that it does, it's a long way out in the future. There is not a lot of necessity for Micron, at least over the next 5 years, to be spending a lot of money on 450mm. 42. There is a lot of investment that needs to go on in the equipment community to make that happen. And their value at the end of the day so that customers would buy that equipment, I think, is dubious. 43. As of March 2014, Intel Corporation expected 450mm deployment by 2020, by the end of this decade. 44. Mark Larpegis of SemiEngineering.com reported in mid-2014 that chipmakers had delayed adoption of 450mm for the foreseeable future. According to this report, some observers expected 2018 to 2020, while Dan Hutchison, chief executive of VLSI Research, didn't see 450mm fabs moving into production until 2020 to 2025. 45. The step up to 300mm required major changes, with fully automated factories using 300mm wafers versus barely automated factories for the 200mm wafers. Partly because a fab for 300mm wafers weighs about 7.5 kilograms, 46, when loaded with 25 300mm wafers, whereas Smith weighs about 4.8 kilograms, 47, 48, 18, when loaded with 25 200mm wafers, thus requiring twice the amount of physical strength from factory workers, and increasing fatigue. 300mm FOUPs have handles so that they can be still moved by hand. 450mm FOUPs weigh 45 kilograms, 49, when loaded with 25 450mm wafers, thus cranes are necessary to manually handle the FOUPs, 50, and handles are no longer present in the FAUP. FOUPs are moved around using material handling systems from Murat or Daifuku. These major investments were undertaken in the economic downturn following the dot-com bubble, resulting in huge resistance to upgrading to 450mm by the original time frame. On the ramp up to 450mm, the crystal ingots will be 3 times heavier, total weight a metric ton, and take 4 times longer to cool, and the process time will be double. 51. All told, the development of 450mm wafers requires significant engineering, time, and cost to overcome. Analytical die count estimation. In order to minimize the cost per die, manufacturers wish to maximize the number of dies that can be made from a single wafer. Dies always have a square or rectangular shape due to the constraint of wafer dicing. In general, this is a computationally complex problem with no analytical solution, dependent on both the area of the dies as well as their aspect ratio, square or rectangular, and other considerations such as the width of scribble in or saw lane, and additional space occupied by alignment and test structures. Note that gross DPW formulas account only for wafer area that is lost because it cannot be used to make physically complete dies. Gross DPW calculations do not account for yield loss due to defects or parametric issues. Wafer maps showing fully patterned dies and partially patterned dies which don't fully lie within the wafer. Nevertheless, the number of gross die per wafer, DPW, can be estimated starting with the first order approximation or floor function of wafer to die area ratio, where is the wafer diameter, typically in millimeter. The size of each die, millimeter 2, including the width of thescribalin, or in the case of a saw lane, the kerf plus a tolerance. This formula simply states that the number of dies which can fit on the wafer cannot exceed the area of the wafer divided by the area of each individual die. It will always overestimate the true best case gross DPW, since it includes the area of partially patterned dies which do not fully lie on the wafer surface. See figure. These partially patterned dies don't represent complete ICS, so they cannot be sold as functional parts. Refinements of this simple formula typically add an edge correction to account for partial dies on the edge, which in general will be more significant when the area of the die is large compared to the total area of the wafer. In the other limiting case, infinitesimally small dies or infinitely large wafers, the edge correction is negligible. The correction factor or correction term generally takes one of the forms cited by de Vries SAD Smiley 52, area ratio circumference / die diagonal length, or area ratio scaled by an exponential factor, or area ratio scaled by a polynomial factor. Studies comparing these analytical formulas to brute force computational results show that the formulas can be made more accurate. Over. Practical.
Yes, I still need to put to Dennis video public. Should we do that? It's Friday evening. Maybe someone likes to watch. Then I have to update my read lists, my playlists. Everything is public. It's 9 p.m. in 8 minutes. Continue.
Ranges of die sizes and aspect ratios. By adjusting the coefficients of corrections to values above or below unity, and by replacing the linear die dimension with average side length, in the case of dies with large aspect ratios. SAD Smiley 52. Or compound semiconductors. While silicon is the prevalent material for wafers used in the electronics industry, other compound 3V or 2,6 materials have also been employed. Gallium arsenide, GaAs, a 3V semiconductor produced via the Czochralski method, gallium nitride, GaN, and silicon carbide, SiC, are also common wafer materials, with GaN and sapphire being extensively used in lead manufacturing. 8. See also. Die preparation. Epitaxial wafer. Epitaxy. Kleber's law. Monocrystalline silicon. Polycrystalline silicon. Rapid thermal processing. RCA clean. Semi-font. silicon on insulator, SOI, wafers. Solar cell. Solar panel. Wafer bonding. References.
Yes, we got 4 minutes left. This is important PDF. I have to add it to my read again list. Yes, it was last added last month. Yes, let's add it, but we got 4 minutes left. And there's some more PDF I would like to read, of course. But that's the semiconductor fabrication plane. But I don't have to record. I'm sit do all this, but of course every time I'm finished reading, I have to update my papers. I will put this on my read again list, Wafer. That's important. We have to electronics. I'll add it to my read again list. Now let's read about this semiconductor planes, something like that. But I have to search it on
Wafer electronics.
On Wikipedia. Find it, but we only have like 3 minutes left. I will close this PDF. Open Wikipedia there. So, but I have to sit do this. No, but I think I will do it without camcorder because I have it super hot. Go to my kitchen with this bowl and take some cola. The video splits in 2 minutes. I cannot do this in 2 minutes. I need some time to do this. To read for myself. I cannot do this in less than 2 minutes. So let's not going to eat more candy tonight. So it's 9 p.m. I will charge the camcorder and start upload this. Then I will look this Wafer PDF and find this semiconductor planes. I cannot do that on 1 minute. The video splits in 1 minute. So I will do that.